Welcome to Study Loop.
Okay, so this problem is on the Milky Way, from the Milky Way chapter on two different forms of energy, thermal and magnetic. So we want to first estimate the thermal energy of the thermal energy density, which of course has to do with volume as well. So thermal energy density of hydrogen gas in the disk of the Milky Way. So this will be thermal energy over the volume of the disk. And so thermal energy is 3/2 times kT, K being Boltzmann constant, T being temperature, times N, which is the number of atoms of hydrogen. So in this case, N is mass of the gas over mass of a single hydrogen atom. And so this would be 5 times 10 to the 9 solar masses, which means, let's rewrite that in terms of grams. 5 times 10 to the 9 times 1.9 times 10 to the 33 grams over mass of a hydrogen atom, that's 1.67 times 10 to the minus 24 grams, giving you something that's very close to 6 times 10 to the 66 atoms. That's your N over there. T is already assumed to be 15 Kelvin over the volume. And now, so for the volume, you got to realize that this is a cylinder we're talking about, right? The disk has a cylindrical geometry, and so the cylinder has a radius r and a height h. So that's the disk of the Milky Way. And so volume of a cylinder is pi r squared h. Therefore, thermal energy density is equal to 3/2 nkt over pi r squared h. That's 3/2 times 6 times 10 to the 66 atoms times Boltzmann constant, 1.38 times 10 to the minus 16 in CGS units, times 15 degrees Kelvin for ISM hydrogen gas temperature, over pi times r squared, that's 8,000, r is 8,000 parsecs squared, times h, which is 160 parsecs, times the conversion from parsec to centimeters, which is 3 times 10 to the 18 centimeters per parsec, and you're going to cube that because of three different times that you're doing this here. And therefore, when all is said and done, the thermal energy density is about 2.1 times 10 to the minus 14 ergs per centimeter cubed. For part B, use blue here, part B, you have the formula for magnetic energy density. It's B squared, magnetic field strength squared, over 2 times constant omega mu naught. And so from an earlier chapter of the book, the magnetic field of the ISM, Milky Way, is about 4 times 10 to the minus 10 Tesla in SI units. Remember, Gauss is the CGS equivalent, and that's divided by 2 times 4 pi times 10 to the minus 7, and this is also in SI units. So this gives you a number that is very close to 6.4 times 10 to the minus 4 joules per meter cubed. You have to convert this to SI units, and so as it turns out, the conversion is fairly straightforward. You multiply this by 10, and you get 6.4 times 10 to the minus 13 ergs per centimeter cubed. for the energy density, magnetic energy density. Therefore, the magnetic energy density is about 30 times the thermal energy density, meaning that magnetic fields will be important, should be important in the Milky Way's ISM. And that's it.